Implementing AI activation functions. Why flexibility, area, and performance are traded off in AI inferencing designs. Activation functions play a critical role in AI inference, helping to ferret out nonlinear behaviors in AI models. This makes them an integral part of any neural network, but nonlinear functions can be fudgy to built-in silicon. Is it better to have a CPU calculate them? Should hardware functions units be written down to execute them? Or would I look at table LUT surface? Most architectures include some sort of hardware implementation, but different neural processors make different choices on how the hardware should look. It's all about the application that the processor will suffer, which sets up the relative importance of cost, performance, and generalities. Activation functions react non-linearly to their inputs, controlling how the information flows between layers, which is somewhat akin to the activation or firing of the neurons in the brain. Satyasande Phakki, senior software architect in Cadence Silicon Solution Groups. Without a nonlinear function in the pipeline, a basic deep neural network would be one giant linear system that could be solved in a large go, but it would reveal only linear relationships. Non-linearities are some make neural networks do interesting things, said Parlik. Without them, a neural network, no matter how deep or large, would be unable to capture complex relationships between its input and output. One way to think about this is that training fits data to a curve. Activation functions specify those curves, and the question is which curve gives the best fit. A linear function would fit the data only to straight line, whereas nonlinear functions can capture more interesting behaviors. The curve of your activation functions is introducing that nonlinearity and what's going to map into your endpoint and data points will be the weights at the different levels. Explained Loss Klein, Program Director for the High-Level Synthesis Division at GMS CDA. Different layers can have different activation functions, but a given layer will have a fixed function established prior to training. Picking the right nonlinear function. Although activation functions must be nonlinear, not just any nonlinear function will do. Activation functions have listed three basic requirements beyond nonlinearity. They must be relatively easy to compute. They must be smoothly differentiable for training, and the derivative must be relatively easy to compute. A more subtle requirement is that they should not suffer from what called the vanishing gradient problem, where training can slow or stop due to some weight being exponentially smaller than alpha after repeated multiplication. Only examples such as the sigmoid and hyperbolic tangent functions suffered from this issue. That aside, a model architect play with the different functions to improve accuracy. The process appears to be at least partially empirical, and over time, different functions have risen to the fore. ReLU, ReLU, turned out to work pretty well in early models, and is still popular now. It's a simple function that zeroes out the result when the input is negative, and passes on the input when positive. It's easy to calculate, and while it's not technically smooth at zero, it's still easy to determine the derivative on the either side of zero. In the early stage of neural networks, sigmoid and tan H-word function, the common activation functions with two important characteristics. They are smooth, differentiable functions with a range between 0 to 1 and -1 to 1, respectively, said Parikh. However, it was a simple rectified linear unit ReLU that ushered into the current revolution, starting with AlexNet. A key advantage of ReLU over sigmoid and Tanite was overcoming the vanishing gradient problem. Many improved activation functions have been used, keeping the basic idea of ReLU, using a self-gating function between 0 and 2, 0 and 1, but with a smooth function and aligned negative values. These include functions like SILU, Swish, and YeLU, Parikh said. More recently, gated activated have gained popularity by introducing an additional gating mechanism to control information flowing through the network. These are similar to the gates used in recurrent neural networks and include GLUE, YeLU, and SWIGLU. Functions vary widely. Table 1 shows several popular activation functions, including two that suffer from the vanishing gradient problem, as from the formulas such as these that questions of implementation arises. Sigmoid, tan H, ReLU, liquid ReLU, YeLU, GELU. Table 1. Examples of activation functions, ranging from the simple to complex. Source: Semiconductor Engineering. As the below shows, the complexity of the functions varies widely. The GAL function, in particular, has alternative approximation that are simply calculation. However, their utility depends on how critical accuracy is. Swish combines both sigmoid and tan functions. The large and growing number of activation functions poses a challenge, particularly for low-power embedded accelerators and DSPs, which focus on efficient fixed-point inference, noted Parikh. The hardware needs to be both flexible enough to handle evolving activation functions with good accuracy while remaining efficient. In theory, it would be nice if an augmentation to the training process is able to monitor the effectiveness of the choosing functions and suggest an alternative. Could you have AI that are trained to find the optimal activation functions for a particular design or for a particular layer? Client said it could watch the training process and say, if we wiggle this one way or another, we can get an activation function that is gonna better fit this set of data. No such capability is available today. 3 implementation options are available, all of which have been employed in different chips, having CPU performance the calculation, the building of functions in hardware, and approximating the functions using lookup tables, LUTs. The best one depends both on the environment, data center versus deeply embedded, and the requirements of the application. Three alternative ways to execute. A CPU can handle any function with accuracy and limited only by the number system and CPU functions unit. Generality is the main benefit of this approach. If a new activation function becomes popular, even existing deployed units could migrate to it through a software update. In a data center, this can be viable. If we're in the data center and we've got lots of CPUs at our disposal, the activation functions usually aren't a big part of the overall computation, and doing them on CPU is quick, no decline. With edge implementation, however, performance will suffer depending on the primitives available in the CPU architecture, and a limited number of CPUs would likely to be a bottleneck for any sizable model. Finally, power would suffer, given the number of cycles necessary for some of functions. From a silicon area standpoint, it's likely the system already will have the least at one CPU, so it would come from free but likely to be a bottleneck. Hardened circuit can turn out result far more quickly than a CPU can, potentially in as little as a little single clock, depending on the circuit design and the clock rate. But they require dedicated silicon area for each whose target application is tightly focused. A single activation function can serve with many parallel units as necessary to complete the activation quickly. Hard silicon is useful when you're trying to get performance and low power, said Sheldon Cole, chief scientist and co-founder of Xpedra. We call this fusion of operators, and then a hardened fusion. That's beneficial when you know the activation function is gonna be a 40% of the execution time, and I need to get it down to 10%. Efficiency is determined by the number, format, and circular design. Power also likely benefits. In theory, the much larger and more energy-hungry CPU could even sleep while the circuit compute functions, and a single function should require far less energy than a CPU. Once shipped, however, that chip will not able to pivot to a new activation functions in the future. ReLU is cheap and easy. The ReLU function is particularly attractive in the hardware because it consists of a multiplexer. This helps explain why the ReLU is so popular, even if the functions might given slightly more accurate result. When ReLU is our activation function, it just says is the number greater than 0? Great, use the number, or else use 0, said Klein. Just 3 lines of dialogue, and works in a bunch of cases, but sometimes it doesn't. What I'm doing with our customers is helping them migrate those algorithms off the CPU into dedicated hardware. If we have to do a lot of floating point math, you end up with really big and slow implementations. So the activation function that I most often use is plain old ReLU. As a result, many models use nothing but ReLU, and that was standard for many of the early vision models. With the exception of YOLO models, you have only ReLUs, said Nigel Drago, co-founder and CTO at Quadri. The third option is the approximated data function using a LUT. Since this can be just a simple small echelon lookup, especially for embedded models that have been quantized to the pure input, performance should be fast. The benefit of the LUT is that it provides the ultimate inflexibility, possibly more than a CPU. So the ability to reprogram a LUT for new function gives the generality necessary for inference engines that anticipate a long life with a variety workloads. This came in handy for the YOLO models Greg mentioned. When you get into YOLO, YOLO, where they have a JALU and its variants, you can implement them that going through the floating point math using lookup table. He said, in embedded models, LUT may require more precision than matrix multiplications. Convolution. Matrix multiplies and other linear operations in large neural networks can easily be quantized to 8-bit or even 4-bit, noted Paklik. But no linear functions are much harder to quantize and often requires high prior precision. Larger LUTs may not be free lunch. However, as you're scaling the lookup to higher bit precision values of different data types, a LUT might not be always work based on the curve fit, said Cole, Chola. If it's not always monotonically increasing or decreasing curve, then the accuracy becomes challenging. At higher precisions, the table can large, and so it's worth investigating techniques to reduce table size without significant trading of accuracy. Fusing activation functions with preceding computation operators like convolution, matrix multiply, element-wise ops, and etc. allows the use of higher precision for the activation computations without increasing storage or memory bandwidth. Variations on LUTs. One could even tier the LUTs based on accuracy and choosing accordingly. You can have a lookup table that's super fast and power efficient. Explained Chol. Then you can have a second level table that may slightly slower, but you can still get better precision. Then you can build a third table that's exact. Depending on the layer specific precision needs, you can decide what type of lookup table to use. Reliability also be helpful in architectures and structures around specific models. In such cases, no hardware is associated with any particular layer, so resources must be allotable as layers progress. If the layers had different activation functions, then a LUT serving both layers would require rewriting when switching functions. If we were doing a lookup table, then we would populate that lookup table on a per layer basis, said Klein. If, on the other hand, either a single function serves every layer in a model, or hardware were allocated by layer, a ROM LUT could be possible. Such an implementation wouldn't permit future updated activation functions, however. Non-trivial embedded models. CPUs aren't typically employed because of performance hit. Even the activation functions make up a small percentage of the overall inference work. That leaves hardened circuits and LUTs as the most common edge approach. If we are talking the entire implementation down into hardware, we don't have a floating point multiplier anymore, explained Klein. We don't have a math coprocessor lying around. We want to take advantage of things that will easily translate into hardware or simple lookup tables and simple operations on the output of those lookup tables. And that's gonna give us a very fast, efficient implementation down in hardware. It can't come down to the notion of good enough, as Expedra found for vision models. You can run your images and then look at the output and see if the accuracy is sufficient, said Prem Tevendran, Director of Software Engineering at Expedra. If you have to put in an FP16 function just for activation layer, it takes up area, and that often isn't worth it. So designers say, we'll just use the LUT. Targeted versus general. AI can serve for a wide range of computing tasks, and the list is growing by the hour. The number of activation function options is also growing, although some of the few functions are motivated by new types of neural networks, such as the prevalent LLM models, LLM today. Deciding on a suitable implementation will depend strongly on the nature of application. Some systems specify narrowly targeted behavior. An inspection tool requiring AI recognize images as representing good or bad units has a very specific brief. It must do one new things for all its life. The model itself could be updated in new ways that provide better accuracy over time. But as long as the chosen activation function remained the same, a hardware implementation could serve well, gaining higher performance and low power at the expense of flexibility that it doesn't need. At the other end of the workload spectrum, an inference engine for use in a data center must take on all comers, and there is no predicting what will be in the models. Any of our approaches could work there. Edge architectures could also straddle and hardware analytic techniques and provide a function unit for the most popular functions and extra LUT for anything new that might arise. So the function unit to be more accurate, but the LUT could be enough to keep the engine relevant and extend its lifetime. This would come, of course, at the expense of the silicon area. But given the cost of some of these chips, a little extra silicon could pay for itself by putting off the necessary purchase of the new board. No one right answer. In practice, architects make the hardware LUT decision differently, according to their perception of their target market, and particularly at the edge. Some embedded systems include hardware units. Others turn to LUTs. Clearly, each believes in chosen approach. And as of now, we don't appear to be done finding new functions. The question comes back to how easy they will be for edge implementation. We were constantly going to be investing new ones because you could slightly modify the curve and get a slightly better answer out of the network, said Klein. The data scientists are always gonna want a more complicated curve, and they are gonna wanna adjust it a little bit to get the slight additional accuracy. On the deeply embedded side, you're gonna look at it the other way and say, well, how can we simplify this? That said, some say that your functions will build off the mathematical pieces of older ones. If you look at the ONS operator list, it has it hasn't been growing even linearly in the last 6 years, said Cho. So we are not creating new operators or new math. What we are doing is changing the way the operators are composed. At least one internet source lists more than 80 possible activation functions, most of which are obscure. If the industry settles on a few standard functions, then the hardware would likely provide the most accurate, highest performance result. SRAM LUT can still provide quick answers, and it may give the architect a better night's sleep knowing that, were a change to come, they could handle it. But it's still early days. There is still much research underway, not just about the activation functions, but about everything involved in AI. So it's likely we'll see a mix of implementations for quite some time. Okay, today I read this article, Implementing AI Activation Functions. Thank you for your time. See you next time.